Hello everyone. Today we'll be looking at the mathematics behind the paper Real-Time Polygonal Area Lights with Linearly Transformed Cosines by Heitz et al. From 2016. We'll be diving into the mathematics quite a bit, so expect the audience to be somewhat familiar with vector calculus. First, let's see what the end goal of this work is like in action. I've coded a little C++ demo here, which shows a rectangular light, and the light emitted from this rectangle is affecting kind of a lot of different complex geometry throughout this scene. It's doing so in real time, which means that we have about 6 to 16 milliseconds to calculate what the scene is going to look like each frame. It's also able to deal with different materials like this shiny gold marking as well as the diffuse green fabric of the banner. To understand what's happening here a little better, consider that we're trying to decide what the color of this pixel here is going to be. We know what its position is in 3D space, as well as its surface normal, and a function called the BRDF, which is associated with the material of what constitutes this surface. The BRDF is a function which tells us how much of a light coming in from a certain direction is reflected back into our eyes. And so, if we project this rectangle onto a sphere centered around this point, and we integrate the BRDF over this polygon, it will determine all of the light coming in from the rectangle, which is reflected back into our eyes. To express this more mathematically, we'll use a work from the 80s called the rendering equation, which says that the radiance at a position P with surface normal n, viewed from a direction V, is the surface integral over the upper hemisphere, so the top half of the sphere, of the light intensity times the BRDF and the dot product between the light direction and the surface normal. The light intensity in this case is going to be some constant in the polygon and 0 elsewhere if we assume that the polygon is emitting light uniformly across its entire surface. This is an approximation that we're going to have to make in order for the calculations to be fast. The key contribution of this paper is that if we define a function called the cosine lobe, which is described as such, the integral of this cosine lobe is going to be the same as a linearly transformed cosine lobe so long as the light is also transformed in the same way. Therefore, we can express certain other BRDFs in terms of a matrix multiplication of the cosine lobe. Going back to our rendering equation, we see that if we try to force this cosine lobe into the rendering equation, and we assume that the light is uniform, this L becomes this L, and the n dot omega here goes into the n dot omega here, and this BRDF is going to end up being a constant, 1 over pi. Therefore, the color of the pixel will be determined by the following equation of L of the surface integral over the spherical polygon, d omega, and this is sometimes referred to as the irradiance at a surface, which is alternatively expressed as L over pi, the surface integral over the spherical polygon, cosine theta, where theta is the angle between the surface normal and the incoming light direction.
The question now is the calculation of irradiance, which is equivalent to this equation. This form is much better for us, as we have reduced an area integral into a summation along each edge of the spherical polygon. This can be run on a computer in real time. To prove this equation, we can first simplify the situation. Consider the irradiance from an area light on a hemisphere. We want to show that the irradiance is essentially the area of the spherical polygon projected onto the unit circle. The cosine term in the definition of irradiance happens to coincide with the integral of the Jacobian of the projection onto the unit circle divided by pi, and can be easily shown as the equation you see on screen. Now, think of a spherical polygon, in this case a triangle. The projected area of the polygon consists of 3 arcs formed by a vector pointing from the origin to the vertices, which then get projected onto the unit circle as well. The area of this triangle is given by A equals theta over 2, as we know from the area of an arc with radius L. The projection is given by n dot product with z, where n is the surface normal vector of the arc. We can then get theta equals a cos vi vj, where v is the direction, and n equals the cross product between Vi and Vj over the modulus of the cross product. By substituting the area into the equation for irradiance, we get E equals 1 over pi times n dot product z all times by A. We can then sum over ij, where j equals I plus 1, except j equals 1 when I equals n for a polygon with n edges or vertices. We get the equation we see here, which gives us a geometric derivation of the irradiance as a series of only 4 sums along each edge for a rectangle. The code for this calculation is very simple, as can be seen here. As a side note, this result can also be provided using Stoke's theorem, which we learned in MM2, but we'll defer that proof to the description below. To sum things up, we have seen how the rendering equation could be simplified into a calculation of irradiance if we assume a cosine lobe based BRDF for the area light. We saw that the cosine lobe could be linearly transformed to approximate other BRDFs and derived an expression for that irradiance which can be computed quickly on a computer.